Okay, so I start by recalling what we did last time, in particular the machine learning workflow, as I like to call it. It's not a standard term, and this is Jean's term. So what is the machine learning workflow? There were 3 main steps. The first one was that I called the 0th step, actually, was to divide the training data into 2 subsets that I call the test set and the training set, okay, such that the intersection of the training and test set is empty. Okay, they have nothing, they have no samples in common. Okay, then the next step, let me remember, was to define a hypothesis class. Okay, so let me call it H. Okay, and the hypothesis class is what? Is a set of functions parameterized by theta. Okay, so it's an infinite set of functions, and our task will be to pick one function into this hypothesis class. Okay, and so how do we do that? We define the cost function, and for this, once this cost function defined, the training is done how? By taking the argmin, okay, of the cost function. So let me, for concreteness, I will I will use the mean square error. So I'm summing over all the samples, so the pairs of inputs and outputs that belong to the training set only. Okay, this is a set of size n train. Okay, and I evaluate the cost between the true outputs and my predictions according to this function that depends on theta. Okay, and this is nothing else than the training error or the in-sample error that I can think as a function of theta. And so the training is this operation or the learning, okay, which is to pick the parameters that minimize the training error, okay? Okay. All right, so once we have done that, okay, how do we evaluate our model? Okay, by computing the test error or the prediction error or the generalization error or the out of sample error. All these are the same thing, which is the cost evaluated, okay, on the test set. Okay. For our function that we trained, okay? And of course, this parameter, here I write it explicitly once, but keep in mind that these parameters here that we obtained are a function of the training set, okay? Because they were obtained as the minimizer of the cost function evaluated on the training set. So if you change the training set, these parameters that you learn are changing, okay? So in this sense, these parameters are stochastic. They're random. They depend randomly in the training set, okay? So here I emphasize that this is a function of the training set. And this is my prediction for the sample J on the test set, okay? This is the test error, okay? And what we what we are aiming for is to find a model, so function in our hypothesis class that has a low test error, low prediction error, okay? Because again, machine learning is about prediction, not about fitting, okay? So what I would like to do today is, so today will be the most theoretical course, let's say, so don't get scared, there will be a question. Today we'll do an actual proof of very beautiful fact. So stay with me, it will not be difficult, it's just a matter of understanding every step, and I will do that slowly. But conceptually, it's very rich, what we'll do today, and very deep, but mathematically, it's very simple, okay? You just have to hang on. So what we want to do is to understand this notion of bias variance trade-off, which concretely means what? We will see that even if all this machine learning workflow is a priori a very complex procedure in the sense that there is a lot of sources of randomness, the training data, the test data. Here I'm considering a generic function in my hypothesis class. A priori, all that is a recipe, but how to analyze that concretely as theoreticians, okay, how to do math with that seems a bit difficult, but actually I will show you today that we can say something very fundamental and very general about this test error, this prediction error, that is obtained according to this machine learning workflow, okay? And what we will understand is this notion of trade-off between bias and variance. I will tell you what means bias and variance, okay? So before entering the actual proof of the bias variance trade-off, let's discuss what it actually means. So you remember when we played with this notebook and we did polynomial regression, we noticed that even if the true model that generated our data, so the true rule that connects the inputs and the outputs is, let's say, a 10th order polynomial, so a rather complex function, we noticed that it was actually better to use a third order polynomial, for example. And this was coming from the fact that we have access only to a finite amount of data, and this data is noisy. And therefore, if you try to use a too complex model, what you will do is very quickly you will fit the noise instead of the actual pattern which connects inputs and outputs. Okay, so this is called overfitting. While if we were using a simpler model with less degrees of freedom, less parameters that are free in the model, so a more restricted hypothesis class, we observed that it was more robust to noise, and therefore it was leading to better prediction error, okay? Even if the true model was a 10th-order polynomial. It was better to use a lower-order polynomial for our model, okay? So we want to understand this fact today. Why is that the case, okay? So I will start with some illustrations that are found in the notes that you have access to, okay? I will comment them and then I will do the proof, okay? All right, so this is the first illustration I want to discuss. So what is that? This represents on the y-axis you have the error, and on the x-axis you have the number of data points that you have access to, okay, in your training data, okay? And so a very generic picture that you would obtain in essentially any machine learning problem is this. So let's see what this means. It means, so the first thing to notice is that if you increase the number of training samples, what you generally notice is first, if you remember our experiments, what happens is that actually at the very beginning, you have a drop in the training error, and then it increases like this. So what is this drop here? Where is this drop coming from? here they don't show it because they assume that we are already in a regime where we have a lot of training data. But in reality, if you have a very small amount of training data, what you first observe as you increase the number of data points is that the training error will be small and then will increase. And why you have first a decrease? Because given some model that you use for training, here the model is fixed. We have chosen an hypothesis class. Okay. And we are training our model in this hypothesis class. If you have a very small number of data points, even if your hypothesis class is rather simple, you will be able to fit all the training data. You remember when we were using, for example, a 10-order polynomial, which is at the end a very simple function compared to much more advanced models that like neural networks or other things. And we had less or equal than 10 data points, we were able to pass through all the data points, remember? Because we just had 10 degrees of freedom, 10 data points, so we could find a function, 10-order polynomial, fitting them all. And this is this decrease here in training error. Okay. Actually, you can even touch 0 before increasing again. Okay. This is what we were observing. But then this increase is due to what? So you are increasing the number of data points. And what happens is that you start to see the limits of your model. In the sense that here, this plot is in a case that I called non-realizable. It means that the true model, the true function that connects inputs and outputs does not belong to the hypothesis class. Okay, so you cannot find a function in your hypothesis class able to really capture the true link between inputs and outputs. And so if you increase the number of data points, what you observe is this mismatch. You see that you start to see the limits of your model. You will not be able to perfectly capture all the points in the training data, okay? And as you increase the number of data points, it reaches a plateau like this, it becomes flat, okay? And at the same time, what happens if you were to plot the prediction error that you would obtain on the test set according to your model for a given number of data points in the training data, and you increase the number of data points, you would see the test error would decrease, okay? Because of course, as you are given more and more training data, you are better and better at generalizing because you are capturing more and more features of the true rule, okay, that connects inputs to outputs, okay? And as the number of training points goes to infinity, these two curves at some point would match, okay? They would reach a plateau and stay constant, okay, in the limits of infinitely many training samples. And this error here, okay, this ultimate error that you cannot beat with this hypothesis class is called the bias. This bias is what? It's the best error you can aim for given that you are using a model in this hypothesis class, okay? So this quantifies, if you want, it's a quantification of the mismatch between the best function in this class and the true function that connects inputs to outputs, okay? So in the case where you would be in the realizable setting, which means that the function does belong to the hypothesis class, this bias would be 0. If you had enough training data, at some point, you could completely learn the function. And because this function belongs to your hypothesis class, you would completely capture it. And you would have no mismatch between what you learned and the actual function. The bias would be 0. But in general, this is not the case. Okay. Okay. And now you have another important quantity, which is here, which is for a finite number of data points of training samples. It is the difference between this bias, which is the asymptotic error you will reach, asymptotic in the sense of having infinitely many training data points, and the error that you actually reach for a finite number of data points. Okay, and this is called the variance. And what does it quantify? It quantifies the error between the best function in your hypothesis class, the one you would learn if you had infinitely many data points, okay? And it would lead to an error equal to the bias here. And the function that you are actually learning for a finite number of data points, okay? You see that you have a difference here between the bias and the variance. And this difference quantifies how far you are in terms of performance of the best function in the hypothesis class. Okay? And again, best function in the hypothesis class means the one you would learn if you had access to infinitely many training samples. Okay? And so this is completely general. Okay? You will always be able to decompose the training error, the test error, which is in red here, into two terms. One, which is the variance. So for a finite number of training samples here, you have this, which is the variance, which quantifies how far you are from the best function in your hypothesis class. And the bias, which is the performance you would reach with the best function in your hypothesis class. And to what is due this variance? This variance is due to what we call sampling noise. Okay, this is a consequence of what we call the sampling noise. And sampling noise means what? Means that you have finitely many data points to train your model. And because these data points are random, you have stochasticity, okay? They do not completely capture the rule or the probability distribution that generated data. It is just a finite sample. And therefore, you make some error due to this stochasticity, due to the fact that you have just, let's say, 1,000 data points instead of infinitely many. And this error is what we call the variance, okay? Okay. Is there a question? Okay, last thing I want to mention here, the difference here between the training error and the test error is a quantification of what we call the overfitting. Because if the difference between training and test error is high, it means that the performance that you get on the training data is very different than what you get on the test data. Which means what? Which means that on the training data, you are actually mostly fitting noise, something which you will not find, let's say you will not find the same patterns in the test data because this is pure noise. Okay, so if this difference between training and test error is high, you are in highly overfitted regime. You are fitting mostly noise. While you see, if you have very many data points and you are here where the difference between training error and test error is very small, it means that the performance that you observe on the training data is extremely representing what you would get on new fresh data, which means on the test data, which means that your model did not capture the pure randomness in the training data. It did not capture this noise. It captured only things that are found also on new data, on the test data, which means actual features of the data, which means something connected to the true rule connecting input and output. Okay, so you're not overfitting in this region. Okay.
But I'm wondering, because the text data also contain the noise, right?
Mm-hmm.
So how can we say that when the error between the test data and the training data is more, so that it's not overfitting? Or
Because so there is noise in the training data, but imagine that I give you infinitely, like a very large amount of training data. This noise will be averaged out if you want, okay? If you are training a model on a very large amount of data, the only thing you will capture are things that are statistically present in all the data points, while the noise is something purely random that depends on the data points, okay? So here, if the test error and the training error are small, it means that you get the same performance on both of them, which means that what you captured cannot be related to the randomness of the training data. Otherwise, you would not, I mean, this randomness will not be, it will not be the same randomness, the same realization of the noise in the test data. So if you were fitting this, it would lead to errors on the test data. While you see if the performance on the two sets is the same, it means really that what you capture is not noise. It's actual information about the model. Is it clear?
yes.
Okay. Let me close the window. Okay. So here is another representation of the bias variance trade-off. And what is that? Now we so here in this plot, we fixed the hypothesis class, okay, and we were changing the number of data points, okay. Now we do something else. We fix the number of data points and therefore the number of training points, training samples and test samples, okay, are fixed. But here, what we vary along the x-axis is the hypothesis class, is the richness of the hypothesis class, okay? And again, we plot the test error in red. So what do I mean by richness or complexity of the model or of the hypothesis class? You can, this is often a notion which is not easy to define. It depends on what type of model you are talking about. But broadly speaking, the model complexity means essentially the number of parameters that you can fit in your model. So typically, if your hypothesis class is defined by theta, which is a m-dimensional vector, an hypothesis class with m1 less than m2 is less complex. So the hypothesis class with m1 is less complex or less rich than the hypothesis class with m2. When we're doing polynomial regression, the hypothesis class of third order polynomials has 4 degrees of freedom that you can fit. It is less complex, less rich than the class of 10th order polynomial, which had 11 parameters to fit. Okay. All right. So we fixed the training, the size of the training data. Okay. And we consider richer and richer hypothesis classes. What happens is that something highly non-trivial, the generalization error is a non-monotone curve. Okay. So it will typically decrease. And when I say typically, it means essentially always. It will first decrease. If you start from models which are here completely trivial model, okay, and here extremely rich models. For completely trivial model, you will not be able to predict anything. You are not able to capture anything about the true relations between inputs and outputs. And as you increase the model complexity, you are able to capture more and more features of the actual true function connecting inputs and outputs. And here there is a moment where you have a point where the gradient is 0. Okay, you have a minimum. And then it increases again. Okay, and this is a priori unexpected. You could think naively that if you increase the model complexity, you have more and more degrees of freedom to fit your data. You will do better because you can capture richer functions. But this is wrong. And this is what we tried to understand last time with our experiments, because at some point, your model becomes extremely sensitive to the sampling noise, to the randomness inherent to the fact that you have finitely many data points and that this data is noisy. Okay, that we call globally, the fact that it's finite and noisy, we call that the sampling noise. We put that under the same name. And what is happening is that we remember that the training error is a sum of two components, always, the bias and the variance. And what happens is to understand this non-monotone behavior, we can plot, okay, the bias and the variance, at least conceptually, because it's not something you can access a priori, but we will see in 5 minutes that we can compute things, and this is really beautiful. But let's say we could compute this bias and variance. What the behavior, the genetic behavior is the following. The bias is always a decreasing function of the model complexity. And this is very natural. And actually your naive guess, if you don't really think about it, the naive guess that tells you that the prediction error would only get better when you increase the model complexity, which is wrong. But this naive guess is actually coming from the fact that the curve you have in mind is this bias, which is decreasing. This tells you what? This tells you that as you increase your model complexity, if you had access to infinitely many data points to train your model, which means you could completely capture, could completely average out the noise of the data, there would be no more sampling noise. Then as the model complexity increases, you can capture richer and richer rules, functions f true. Okay, you can get closer to the true function because your hypothesis class is getting bigger and bigger. And so you can get closer and closer to the actual function you are trying to learn. Okay. So the bias always decreases when the model complexity increases. But there is a price that you pay when you increase the model complexity. And the price that you pay is that instead the variance is a monotone increasing function of the model complexity. And again, what is the variance? The variance is a measure of the sensitivity of your model to sampling noise. And here we said that the training data is fixed. So the sampling noise is what it is. We have, let's say, 10,000 data points to train, and we have no more. So we have to deal with that. And this data is imperfect. It is corrupted by noise. It is finite. We have to deal with that. But if you start to increase too much your model complexity, you will start to fit the noise that is contained in your data. So you are overfitting above a certain point, which means that you are capturing more patterns coming purely from the noise than features which are actually connected to the function that you are trying to capture, the true rule between input and output. Okay. And so there is a sweet spot, there is a trade-off, which is really here. There is a optimal model complexity, which is at the same time, which has a bias low enough, which means that it's rich enough to capture most features of this function. Or let's say, it captures it good enough, let's say. And at the same time, it's not oversensitive to noise, so the variance remains low. Okay. So your model is not so rich that you will overfit, and which means mostly capture noise. Okay. There is this sweet spot in between, and this is where you should, what you should aim for. And how to find this optimal model complexity? By cross-validation. How do you do that? Again, let's say you select 3 possible hypothesis classes, like we did, polynomials of order 1, 3, and 10. You train given your finite amount of training data, you train your 3 models, and then you test each of them on your test data, and this fits a number. You evaluate their performance by obtaining the prediction error on this test data. And you should select the one with the lowest prediction error, which means the one which is closest to this sweet spot. Okay. 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 So let me now do a proof. Okay, let's do some mathematics. Okay, here is a final picture. Maybe I can quickly comment it. It's just another representation of the same effect. But imagine that in the space, the abstract space of all possible functions in the universe, of all possible models, okay, there is somewhere here the true model. So this is the true rule that connects an output to an input. Okay. This is this function. Okay, which is somewhere in the rather big space of functions that exist in the world. And you assume 2 possible hypothesis class, which one which is rather simple, okay, and one which is much more complex with many more parameters, 3 parameters to train, and you are given some training data, some finite amount of training data. You train each of these infinitely many functions in the world. Some belong to this complex hypothesis class, which are the green ones, and some belong to the simple hypothesis class, which are the black ones. And what happens is that the low complexity one has a high bias in the sense that it's not rich enough to capture the true functions, which means that in this space of functions, the true model is not part of this hypothesis class here. Okay, so this generates one type of error, which is a bias. Okay, you will never be able, even if you had access to infinitely many data, you will never be able to capture the true model completely. Okay, because you are restricted to this smaller subclass of functions. But at the same time, because this function has less degrees of freedom, if you start to change the training data, okay, so if you start to sample data and each time I give you a new training set and you evaluate your model on this new training set, you get lower fluctuations. Okay, so each realization of your model, each time you train one, you get a new version of your model, a new theta hat, if you want. This theta hat is a function of the training data. So if I change the training data, the theta hat changes, and therefore your predictive power changes. But you see here, the fluctuations are small because the model is not too rich. From one to the next, you are robust to noise, and so you stay close. You basically have always the same performance. Okay, but this performance is not perfect. You have a strong bias. Instead, if you consider a much richer class of functions, which are this huge space of green functions. In theory, you could capture the true model if you had access to infinitely many data points, because the true model belongs to this class. But the problem is that the data is finite, and therefore, for some realization of the training data, maybe you will fall here, okay, due to noise, or maybe you will fall here, or maybe here, okay? And so this quantifies the fluctuations, okay? And so this error, the fact that you have high fluctuations due to the sampling noise, high sensitivity to noise, is what leads to variance, okay? Okay? And in most of the case, it's actually better to have some bias, but a lower variance, because often the type of error that dominates the prediction error is the variance. So it's often better to consider a simpler hypothesis class and to train that, rather than considering very rich models and take the risk of having a high variance, okay, to fit the noise, okay? Okay, and by the way, this distance between the middle and across quantifies essentially how far you are from the true model, and therefore the prediction performance, okay? All right, so let's do some math. Is there any question? No, these are my math. Here. No? Okay. So what we want to do is really to understand something, okay, about this quantity, which is obtained according to this machine learning workflow. Okay. Can we say something general about the prediction error? And magically, yes. And this is actually very beautiful. So you will see the proof is rather simple, but the result is extremely deep. We will obtain this bias variance decomposition. I will show to you, I will prove to you that very generically, the prediction error here, whatever is the hypothesis class here, okay, I will never specify what hypothesis class I'm considering. I will keep it generic. I will don't specify what is the distribution of the data. This will be completely generic as well. Yet I will be able to show you that this error does decompose into the sum of a bias and a variance. Okay, so let's do that. Okay, so let me see if I can do it by heart. If I can remember how it works. I think I do. So the idea is that, okay, of course, we cannot say anything for a specific realization of the training data and all that. Okay, we can only say things in average. We are statisticians. Okay, so let's do statistics. When we do statistics, what we like to compute is an average quantity. Okay, so what I want to compute, really to study, is the average. Okay, that I will denote like this. This means expectation. Okay, of the generalization error. So the expectation with respect to what? What is the randomness here? So this prediction error is a random variable, but random in what? Okay, what fluctuates? This prediction error is a function of the data. Okay, it's a function only of the data. Here you have the test data, and here these learned parameters are a function of the training data. Okay, so the only source of randomness here is the data. So here I will write expectation with respect to the data. Okay, and again, this data, we assume that it is pairs of inputs and outputs, okay, where each input output pair is a random variable, which is drawn independently and identically according to some unknown probability distribution that I will call P. Okay, but I don't need to know what is this probability distribution. I don't care. Okay, it exists. Okay, it may be extremely complicated. And what I concretely means by this expectation here, it's an average over the probability distribution of all these samples in the data. Okay. So concretely, it means expectation with respect to x1, y1, which is distributed according to P, expectation over x2, y2, which is distributed according to P, etc. Okay? This is what I mean by this symbol here. Okay, so let's compute that. So let me concretely write what it means. Okay. And this is our model that we learned, which is a function of the training data, because we learned on the training data. And this is our prediction for the output according to our model. Okay, so I will take the square loss, so the mean square error, okay, a square cost. And in order to concretely say things here, I will assume something, I will assume a generic model for the data. Yes, so will there be caveats with the assumption that the data is IID? So you mean if the data is not IID, is there a problem? This is what you mean? Jonessa?
Here you assume that the data is IID. So, yeah. So I think in real life, data is not independent.
No, but in real life, what do you mean the data? So each sample of the data, or the link between input and output, like inputs and outputs are not independent, of course. This is what we're trying to learn. But each sample, yeah, okay, maybe in real life, each sample is not independent, but this is what we assume. Yeah. Okay. We cannot do anything otherwise. Okay.
And I want to ask this part. You said, okay, I can. EX1, Y1 is distributed according to P, and EX2, Y2.
Mm-hmm.
So the expectation is
over this distribution P for each sample.
It's the same P.
Yeah, it's the same P.
Okay,
this is what I say here. Each sample is distributed according to the same distribution. This is our assumption. Okay.
Okay, thank you.
And actually, I will do another assumption. Okay. Yes.
Yeah. What's the difference between the E infinite and E out? Because E out is the mean square error of the whole data set. Now, according to what you said, or what I understand, E infinite is also the same. You have the same idea.
No, I think you misunderstood. The E infinity is not an error. It's an expectation with respect to the data.
Expectation of error.
Sorry?
The expectation of the error.
So concretely, if you want, like, so let me write concretely what I mean here one time by this expectation. Let's say of a function of the training data, and the training data are samples x I y I, okay, for I equal 1 to n. Concretely, this is an integral over dx1 dy1. So it's an integral over the product from I equal 1 to n of dxi dyi of p of xi. This is the joint distribution of xi yi, okay, of my function that depends on all the xi's yi's. Okay.
Okay.
Concretely, this means that. Okay.
Okay. Good.
All right. So in order to do computations, I will need to assume actually something about this distribution, but something very weak, you will see. So what I will assume is a certain model for the noise. That's all. What do I mean by that? I will assume a Gaussian noise model, which is, like I told you, a very generic model, because Gaussian noise is a kind of universal type of noise. Okay. What does it mean? It means concretely that the relation between the inputs and outputs, okay, can be written in this form. There is a true function, so I could write true here, but let me skip. Okay, I will keep it maybe at the moment. Where this noise variable are IID, and they are drawn according to the normal, the standard normal distribution of mean 0 and variance sigma squared. Is it clear what this means? Okay, it means that the probability distribution, the density of sigma I is of the form of 1 over 2 pi sigma exponential minus 1 over 2 sigma squared epsilon I squared. Okay. This is the probability density function of the standard normal distribution of variance sigma squared. Okay. So I will assume nothing on this function f true. This can be completely general, but I will assume that the noise is additive and Gaussian. Okay. It's the only thing I will assume. And this is a very generic assumption. Okay. All right. So if I do that, okay, what do I obtain? I'm looking at what I wrote here, the expectation of the generalization error. And now I can replace these true labels, okay, the labels in the test data. I can replace their expression according to this model that we assumed here. And be careful, when I say the model we assume, I'm not talking about the hypothesis class that we are considering for the training and so on and so forth. I'm just assuming a mathematical model for the way the true labels are generated conditional on the inputs, given the inputs. Okay. So this is a mathematical model for how the inputs and outputs are connected. And in a true machine learning setting, you do not know this function here. You do not know it. Okay, you don't have access to it. We just assume that it has this form plus Gaussian noise as theoreticians that are trying to do a theoretical computation. Okay. All right. The model that we use here for prediction and that we trained is this one, which is not the same. Okay. This can be completely different from the true function here. Okay. All right. So what I obtain is that the expectation with respect to the data of the generalization error is the expectation. Now I will just write these two means the sum over all the samples in the data set, which is what I wrote here, of, so I replace the true label by the mathematical model for its generation plus noise minus our model that we trained, and that depends on the training data. Okay, squared. Okay, now I'm developing the square, and I obtain epsilon I squared, and I'm considering this as a single term that stay together. So I obtain plus this term to the square now I don't write anymore that this theta depends on the training data, but keep it in mind. Okay, plus 2 times the noise times this difference. Okay, and now I use the linearity of the expectation. Okay, this sum is a linear operation. An expectation is a linear operation. So I can switch these two operations and I can put this expectation there. And sorry, I forgot to mention something. I'm also taking the expectation with respect to the noise. Okay. Actually, I don't need this notation, this additional notation, because when I say that I average over the data, of course, it means with respect to the distribution of the data, which contains noise. So it is redundant. It's fine to keep it like this. All right, so here I put the expectation inside, and what do I obtain? It means that I have an expectation here over the noise. Okay. And here I have my expectation over all the randomness in the data, including the noise, including everything. And here I have an expectation. Okay. But here you have to notice something. Is that this object here, this difference, okay, this difference is a function of what? It's a function of the training data through this theta hat, and it's a function of the test inputs, okay, this xj's. So this is the xi's, sorry, this xi's that belong to the test data, okay? But you see that all that does not depend on this noise, which is the noise in the test data. Okay? Nothing depends on this noise. Which means what? Which means that this expectation, which is an expectation over everything, including the noise, including the training data, including the test data, can be decomposed as an expectation over the noise, which comes acting on this variable only. And here I can put an expectation over the rest, which does not include this noise. Okay. But this expectation here, the expectation of this noise, gives what? It gives 0. because the noise is a centered random variable. We assumed that it had 0 mean. Oops. Okay. It has 0 mean, and it is not correlated to this difference here. So when I average, I obtain 0. Okay, so this is the first step of the proof. Which means what? Which means that all that simplifies into I will keep the outside expectation over the test data. Here, I have a sum over the test data. Here, I have an expectation over this random noise to the squared. Plus here, I have an expectation over all the data, which is not the test data. The expectation over the test data, I keep it outside here, okay, because I have a sum over it here. So here it's an expectation over the training data of this thing. Okay, so one big chunk has disappeared due to the fact that the noise in the test data is completely uncorrelated with all the training data. All right, what is this quantity? It is the expectation of the noise to the square. Okay, this is the variance. Because the noise is centered, this is the variance of sigma I. Okay, which by definition is what? Is the mean of sigma I squared minus mean of sigma I to the squared, but this mean is equal to 0. Okay. So here, this is really the variance that appears. And this variance, we called it, sorry, here I'm mixing notations. This should be epsilon. And this variance is what we called sigma squared. You remember the distribution here of the noise is a Gaussian with mean equal to 0 and variance equal to sigma squared. Okay. So this object here is sigma squared. All right. So now what I do is something completely trivial. Okay. I will add and remove one term inside this square here. I will write F true. Okay, that depends on the test sample xi. I will remove the expectation over the training. The expectation over the training data of my model. Okay. I will add again the same thing. So I'm just adding 0. So I can do that always. And I have the last term here. Okay, all that to the square. And now I combine this term with this one and this one with this one. Why? We will understand very soon, because by combining these terms together and computing these expectations, we will see what we obtain is something that we will define as the bias and something which will be the variance. Okay, so let's see. All that gives me an expectation over sum over the test set. of sigma squared plus, so I develop the square. Okay. This is the training data. So I have my first square, which is f true. Okay, and I will just write now x with an index I like this, which means f true applied to the input xi in the test data. Okay, just to make it lighter, minus the expectation of my trained model. Sorry, and I will use the same notation. This squared plus I have another square, which is this. Plus 2 times the product and that's it. So it looks even more complicated, but let's see that it goes, it becomes actually simpler. So first, let me comment on the last term here. What does it give? Can someone try to tell me, by keeping in mind, by tracking what parts depends on what, in the sense that some parts in this product depend on the training data, some parts depend on the test data, maybe some depends on both or not at all, I don't know. Okay, you have to keep track of what depends on what. Here I have an expectation over the training data. How does that simplify? Okay, so also, if this, my notation is not clear for some of you, here you see some of you may be confused because I'm taking an expectation over the training data 3 times, here, here, and here. But it's just that if you want, you can, when I take an expectation, if you want, I'm doing an integral, so I'm summing over dummy variables, right? So this expectation means an integral over dummy variables that are entering this theta hat. Okay. So I can think of this function here as a function of dummy variables, which represent samples from a training data, a training set, and I'm averaging over this training set independently of what I'm doing here or of this expectation. Is that clear?
Can I ask about the previous line?
Yes.
The expectation here is with respect to the test data only.
So here the outside expectation is over the test data. Yeah.
I think in the previous is for the whole data.
Yes, but here I have put the expectation over the rest, which is the training data only, if you want.
Yeah. If we see only D, it means only for the training data.
Yes, but you see, actually, they would know. They would be, yeah. Here, sorry, it's only the training data.
Okay.
Yeah.
Thank you.
So here it's the test. So let's think for a second. Okay. This part here is a function of what? It is the true function applied to a sample from the test data. So it's a function only of the test data, right? And actually in this case of a single input of the test data, okay? This object here is a function of what? It is a function only of the test data as well, because I have averaged over the training data. So it's not anymore a function of the training data. Okay, again, this is an integral over the distribution of the training data. So because I have integrated over the training data and its distribution, it does not depend anymore on the training data. So it's only a function of the test data. Okay, here I'm averaging over all possible training sets for this model. Okay, so I'm averaging my model over all possible realizations of the training data. Okay, and this gives me a kind of average prediction or asymptotic prediction, what I would obtain if I had infinitely many data points. Applied, this is the optimal predictor, the optimal model in my hypothesis class, okay, the one I would obtain with infinitely many data points, applied to a sample from the test data. So it's only a function of the test data, okay? Here is the same. This is just the same as this thing, so it only depends on the test data. And here is a function of what? Of the training data and the test data this time, so all D. Because you see, this one was not averaged over the training data. So it's, here my parameters theta really depend on the training data that I consider, and the average is outside here, is outside of this parenthesis, okay? But you see, because all that, these three terms do not depend on the training data, by linearity of the expectation, this is a linear operation, I can put this expectation here, okay? And what does it give? It gives me, okay, it gives me 0, because you see, this parenthesis gives me, the parenthesis which is there, gives me expectation dtrain of f theta I minus the same thing. Okay? So all that is 0. And essentially I'm done. Let's see what do we get from all this result. Okay, I have an expectation of a square, and I have the expectation of another square, this one, which is the expectation over the training data. Okay.
Perfect. Can I ask something?
Yes, yes.
So in the in the part where you said that it's the expectation over the train, and then you apply it to wait, because I cannot annotate this this the part where it's the expectation over the train of f of theta. You said it's a function of the test,
Yes.
but then in the black ink, it became expectation over the train of f of theta.
Let me try to understand what you say.
It's difficult because I cannot annotate.
Okay, your problem is this, is that here, your problem is that I'm saying that this is a function only on the test data.
The next term,
Here?
it's a function of the test, and then you apply the,
But this one?
yeah, and then
It's the same as this one, huh? They are the same thing.
But in this block, in the equation below, you said it's expectation of the over training set. Okay. Okay.
So what I'm saying is that this thing here alone, okay, is a function of the training data and the test data of everything. But now, because I'm averaging over the training data here, the result is a quantity that depends only on the test data now, because I took an average over the training data. Okay, this you agree?
But the next line.
So it's like I mean what happens? The operation I'm doing here, if you want, it's called a marginalization. It's like if you have a function of x and y, and I'm taking an average over, let's say, x and y have a joint law, and I'm averaging over x, what I obtain is a function of y only. You agree? You have to say me yes or no.
Yeah. But in the next line.
So here I'm doing the same. I'm averaging over a function that depends both on the test and training data. I average over the training data, so the result only depends on the test data. Okay. And now what I'm saying is that because in all these terms here, the only one that depends on the training data is here, is the last one, I can take this expectation and put it right in front here, because it's the only one that depends on the training data, and the expectation is a linear operation, so I can push it inside this parenthesis. Okay, all these things are independent of the training data, so they are just constants with respect to the training data, so I can just push the expectation inside. Okay, and therefore once I have the expectation over the training data here, I obtain something minus the same thing, so I get 0. Okay. All right. While the two first terms here, okay, here and here and here, the three first terms, they are non-zero. They are here. And this is the end of the proof. So now let's analyze this result. Okay. And all that is equal to the expectation over everything, all the randomness of the data, training and test data, and noise of the generalization error. So let's see. There are 3 contributions. The first one, okay. By the way, I can put this expectation here inside because this sum is just a sum over a dummy index. If you want, this is a sum over I equal 1 to n test. Okay, so I will actually put this expectation in front of these terms. And so this is an expectation at the end. These 2 expectations are expectation over everything. Okay. So I have 3 contributions. The first one is the simplest one. It's sigma squared. Okay. And this has a name. It is called the irreducible error. It represents an error that will always be there. It will always be there, whatever is the quality of your learning, whatever is the richness of your model, independently of everything. And this just tells you that you cannot learn pure noise. The noise is completely random. There is nothing to learn. And therefore, if you are trying to predict the outputs, the labels of a rule which is of this form, you will never be able to predict the noise because there is no structure. It is noise. Okay, so you will always make an error on the true labels. And this error is the minimal error is the error that you will do on the noise. Okay. And the error that you do on the noise is the variance of the noise in average. Okay. So this is the irreducible error. We didn't plot it in the curves that we discussed before, but it would just be a constant shift of the prediction error. Okay, if this is non-zero. Then we have a second type of error. Okay, which is the term here. Let me write it. Can someone guess whether this is the bias or the variance? It must be one of the two. And tell me why you think so. Does someone have a
Can I ask? F through is the one from the test.
Is what?
F through is from the test.
No. So no. You have so the F true is the function, is the true function that underlies the relation between inputs and outputs, is the unknown function that you are trying to capture in some way, thanks to machine learning. But it's a function that you don't know, okay? This is a theoretical quantity that we can compute, that we can write down on paper like this as theoreticians, but it's not something you can concretely compute in general. Okay, the F true is unknown to you. Okay, this is the true function that connects the labels and the inputs. the true complex rule that given an image tells you whether there is a cat or a dog on it. It's a very complex abstract rule that maybe there is no way to write using mathematics, but it exists. It's an abstract object. It's completely unknown. Okay.
So is it the bias?
Yes, it is the bias. And actually we call even that the bias square because we have a square here. And why is that the bias square? Because, okay, so this is the bias square. Because you see that it quantifies the mismatch, the difference, the squared difference, the expected square difference. Okay, this is in average over the data. Between a true label, okay, without even noise here, this is the true label, okay, if we would like to predict if there was no noise. And the very best estimate of this label that belongs to our hypothesis class. Why is that the very best estimate, the optimal estimate of our hypothesis class? Because it is our estimate averaged over the training data. Okay, and you can think of this statistical average as the limit of the empirical average, where the number of training sample goes to infinity. Concretely, this is 1 over n. This is the limit when n train goes to infinity. 1 over n train. Okay. Of f theta. That depends. Or actually, okay, it's slightly more complicated. You could write it. Yeah, no, it's correct. You can think of it like this. It's a training set, okay, that depends on n train, and you are looking at the limit of your estimator when you would have access to infinitely many training point, okay? So it's our very best estimate is what we would get if we had access to infinitely many points in our training data. And if our best estimate is still not perfect, is not able to really predict the true labels, then this is what we call a bias. Our model is biased, it's statistically biased, okay? It is not able, even in the best case, to capture truly the true underlying function that connects inputs and outputs, okay? And the third term, which is therefore the variance, I rewrite it. This is the variance. And indeed, we see directly that it is a variance. Why? This is a random variable, which depends on the training data. Okay? It's a random prediction function, random as a function of the training data. While this is its average. So this does not depend on the training data. This is our best estimate in the hypothesis class. And you see that here we are computing the square deviation between this random variable and its expectation. So this defines a variance. Okay. And this quantifies the fluctuations of your predictions due to finite sampling, due to the fact that you have a finite amount of data and that it is noisy. Okay. This estimate in average how far is your model for a given realization of the training data. How far is it from the best model in your hypothesis class, the one you would learn if you had access to infinitely many data points. Okay. And so this quantifies the sensitivity of your model to sampling noise. Okay, so you see that we obtain completely generally that the expected prediction error can be decomposed in 3 terms: the irreducible error, which is not very interesting. This is just a number that depends on the noise. And 2 terms that are much more deep. One is the bias, which quantifies how far your best prediction function in your hypothesis class would be from the true function. And the variance, which quantifies the sensitivity of your model to finite sampling. Okay, what are the fluctuations of your model? How your model fluctuates strongly or not due to finite sampling, due to the fact that you have finitely many data points and that it is noisy. Okay. That's everything I wanted to say. Let me emphasize that all this computation, maybe you didn't grasp everything right now, which is fine. But I really want to strongly emphasize that this computation is not complicated at all. There is nothing mathematically. I just used the linearity of the expectation, and that's it. What is non-trivial in all this computation is conceptual. Okay, there are many conceptual steps, okay, that are non-trivial to grasp. It is important to track along the computation which parts depends on what, okay, in order to obtain the final result. And I very strongly suggest you to repeat the computation, to start from the hypothesis here. So the definition of the prediction error, the model that we assume, which is very generic, which is just an additive Gaussian noise, and to try to repeat all steps, okay, in order to cancel the terms that should be canceled and converge to the bias and variance and really understand what is going on, because it's absolutely fundamental. And this is the only mathematical proof and technical in bracket technical result that we'll do in the course. Okay, from now on it will be much more light in terms of mathematics, but I think it's really important that you grasp this result, because this result is really what underlies all the difficulty of machine learning, is this competition between sensitivity of the model to finite sampling, the variance, and the richness of the model, which allows you to capture richer and richer true functions, true relations between input and output, which is the bias. Okay, and the competition between the two is what makes learning difficult. Okay. All right, so put that in your head, and let me just mention a last thing, is that all that in modern machine learning, let's say all that was true, and this is taught for at least 30 years, and this is true in, let's say, the classical regimes of machine learning. Okay, let's say for rather simple machine learning techniques. But now we are living in a world where we are able to run extremely complex machine learning algorithms, which are parameterized by millions, if not billions, of parameters. And it appears, and this is a quite recent discovery, actually, this is really the forefront of machine learning, of theoretical machine learning and practical machine learning. is that people realized that this theory of bias variance trade-off actually collapses, is not true anymore for very complex machine learning models like neural networks. What do I mean by that is that this is an empirical observation, and people now, theoreticians, are trying to understand what is going on, and it is far from clear, and I will not fake that I know enough to explain to you, okay? Because this is not the case, but be aware that there are things now in the literature, and many people study that, which is called, for example, the double descent phenomenon. Okay. Double descent phenomenon, and I will stop there. Don't worry, I just need 4 minutes. Is actually the observation that if you consider very complex model, much more complex than what we did in polynomial regression or whatever, like in modern neural networks with billions of parameters, what happens is that if you plot the generalization error, okay, for a given fixed size of the training data, okay, as before, the test error decreases and increases. So there is here a sweet spot. Okay, the optimal trade-off between bias and variance. So a priori, you should select a model with that complexity. But actually, if you continue to increase the model richness, what really happens is that you have a second decrease. And it happens that actually the minimum that you can reach, at some point you reach a plateau, but the minimum you reach here can be even lower than the minimum you reached here. So this is what we call the double descent. Okay, so what I discussed today is essentially we stopped here. Okay, we studied this regime, statistics, and the bias variance trade-off theory that we did today applies here. Okay. But in reality, you have this second descent of the prediction error, which occurs if you consider extremely complex models. And this may, once we understand a bit what you will get used to this bias variance theory, if you redo this computation, it will look very not natural at all, unexpected, because what I told you is that if you consider models that are too rich, you start to overfit. You are fitting the noise. Okay, in this region here, you are in the region of overfitting, because you have just too many parameters given the amount of data. And so you start to fit the noise. Your model is rich enough to completely fit the noise. While in this regime here, you are in the underfitting regime, which means your model is not rich enough to capture enough features of the true function. You really need to be there. But actually, with more parameters, this reduces the overfitting, which is extremely counterintuitive, and it's counterintuitive not just for me and you, but for everyone right now. And people are trying to understand why is that the case, and it is far from clear. Okay, so if you want to do a PhD on that, you are more than welcome. These are very interesting and recent questions. So don't be shocked if you hear about the double descent. It's not that I was lying to you, it's that these are recent discoveries and people are trying to understand what is going on. Okay. All right. So for example, you see if you check if you let me share my screen. If you Google double descent, you will find many articles now on this kind of things, where you see the test error as a function of the model size, and you see the first descent. And classical statistics, which is what we did today, tells you that you should continue to increase, but actually what happens is that you have a second decrease. And now you have many papers on that, the deep double descent. So this thing happening in deep neural networks and in many other settings. Okay, and so that's very nice. And essentially, this is everything I wanted to say. We'll not do any more statistical learning. What we did today is part of what we call statistical learning. We'll enter more into actual machine learning models. So next time we'll do, Monday, we'll start linear regression and a bit of Bayesian inference. So if you look at the course, the notes, at the moment I will skip the chapter 4, which is on gradient descent. We will do that a bit later. And I will go directly to linear regression and Bayesian inference. Okay, linear regression is what we'll spend the most amount of time on, and then we will move slowly towards neural networks. But please read about linear regression in the notes. I think it's chapter 5 and then 6. Okay, and I will send you the notebook so that you can start playing with it. Okay, is there any question?
You will focus on icing or diabetes?
I will do both, I think, but I will start with the diabetes. Yes, so we will use linear regression to do predictions about characteristics of patients given their medical history. Yeah, so I will send you the notebook right now that I update.
Yeah. Can I ask about in the calculation that we did? It is because the input and output are they are distributed from a probability distribution. So what about if, for example, like a logistic regression,
Mm-hmm.
where the output is like you cannot quantify the difference between the output and the output from the model? Do you understand?
I'm not sure to understand.
I have a problem with how to quantify, how to measure the error if the output are labels.
If there are labels, so outputs are always labels. You mean if they are discrete? Or...
No, more of you cannot measure a difference. You cannot measure a distance between.
Okay, so in which settings do you have in mind?
So if the output are classes, sorry.
You mean if there are not numbers? You mean if there are abstract classes, for example, the outputs could be dogs and cats?
Yeah. You
just need to map these classes onto numbers. You just say you define the class dog to be +1, the associated label should be +1, and cat is -1, for example, or whatever number you want. So you can always map discrete classes onto the natural numbers.
It's hard to imagine if there are more than 2.
Why? If you have 3 classes, you can map onto 0, 1, 2, for example. And actually, we'll discuss that when you have multiple classes like this, you use what we call one-shot vectors. So the output in this case is not anymore a scalar, it's a vector whose size is the number of classes, okay? And the vector is encoding the class by putting a 1 at the location that corresponds to the class, and it has zeros everywhere else. So let's say you have 3 classes, you could encode that thanks to vectors of dimension 3, And the first class would correspond to a vector of 1, 0, 0. The second class would be 0, 1, 0. And the third would be 0, 0, 1. So this is what people do.
So in that case, the form of the bias and the variance should be the same.
Yeah, I mean, if you want, the derivation here does not really depend on what the alphabet of the output. It's generic, and as I told you, if you have one-shot vectors, if you want, instead you can map them onto 0, 1, 2, or whatever numbers you want. It will not change what we did. What we did, you see, does not really depend on the alphabet of Y. It does not depend on anything. It's completely generic. Okay, so if you have 10,000 classes, okay, you can or use one-shot vectors of size 10,000, but you can also map each class onto a different number, and what I wrote applies. Okay, so I'm not saying that all representations are completely equivalent in the sense that the quality of the learning you would get using one representation or another would be the same, but conceptually it's the same. Okay, sometimes there are better representations to use than others, but the derivation we did today is a theoretical result. It's conceptual, and this conceptual derivation you can extrapolate even if the classes are richer than just binary or just one scalar. Okay, it will always be still a decomposition into bias and variance. This will not change. This is universal.
Okay, thank you so much.
Okay, if there are no more questions, we meet on Monday at 11 a.m. Italy time. And for those who are at ICTP, if you have questions, you can come by group in my office, and I can spend some time to help you, no problem. Okay. Just drop me a mail to check that I'm here.